Good afternoon, everyone. So today we have a very important person to me, my PhD advisor from the University of Alberta here, and he'll be talking about stores, agriculture, water sustainability. But before he presents, I'd like to introduce him to you. So he's a professor in the Department of Chemical and Materials Engineering at the University of Alberta. He received his PhD in chemical engineering from the University of California, Los Angeles, and his MSc and BSc from Jinfeng University. Dr. Liu's research interests lie in process systems and control engineering, focusing on developing innovative modeling, estimation, and control methods to tackle the pressing challenges in closed-loop smart irrigation for water sustainability. Dr. Liu has published 3 books, over 200 journal and conference papers, and edited a few special issues. Dr. Liu currently serves as the editor-in-chief for the IChemE journal Digital Chemical Engineering. He also holds roles as an associate editor for several other journals, including the IFAC Journal of Process Control Engineering Practice, International Journal of System Science, and MBPI Journal of Mathematics. Let's introduce Dr. Jinfeng.
Okay, thanks Ben for the introduction. So can you hear me from the back? Okay, that's good. So this is normal. No matter where you go, typically people will tend to sit in the very back. That's okay, right? So as Ben just said, so I'm going to talk about closed-loop irrigation, the work we have done over the past few years. I'd like to show you this map first, just to show you where is Edmonton, where is the University of Alberta, just in case you don't know or you haven't heard about this place or this university before. They're not that far away. It took a quite long time to travel here, okay, a couple of transfers. And also, I'd like to introduce the province a little bit because this is relevant. Okay, it's relevant to the talk we're going to discuss today. So in Canada, all these provinces are huge in terms of land size. Alberta the same, and to the northern part, so we have oil sands. The oil sands industry is one of the key drivers for Canada's economy. So it's over there, and it is mined using very big shovels and trucks instead of the traditional approach. And this is Edmonton in the central Alberta. So in Edmonton, we have the university, and also there's one professional hockey team, one of the NHL team, Edmonton Oilers. If you follow hockey games, you may know this. So the best hockey player of this generation, Conor McDavid, is in this team, just like Messi in soccer. And to the west of the province, we have Rocky Mountains. So Banff National Park is like Yellowstone in US. So it's very beautiful. You see one lifestyle for many, not for many, but for some of the people in Alberta is like this. Get a degree from the university, and find a job related to oil sands, and then watch hockey games after work, and go to Banff National Park for vacations. It's easy, right? But what we are going to discuss today is not related to those parts. It's related to an area here, very south of this province. It's an irrigated agriculture district. For this part, if we zoom in, what we're going to see is these green circles. So I don't know whether you have seen these green circles when you fly from one place to another place. You may have seen these. So many years ago, when I saw these green circles, I didn't know what were those. And later when I moved to Edmonton, I realized, okay, these are farms. Okay, so these farms are indeed very big. They are generated by irrigation systems called the center pivot irrigation system. It's a very, very big irrigation system. You see, using one picture, it's not easy to see the system entirely. So I also put another photo here of the smallest center pivot we could find. So basically it works like this. So we have underground water pipes. The water is pumped to the center of this pivot and then sent to the top pipes and then applied to the farm. And this center pivot, it just rotates around this pivot. So that's why it's called a center pivot irrigation system. Okay. So such a system could be, okay, I think I was out of the camera, but that's okay. So that system is very big. So the arm, the radius, so basically the pipes could be up to 1 kilometer long, typically 300 meters, 500 meters. So it's pretty big. And this is a subject we're going to talk about today. Okay. And this is the outline of the talk. So today we're going to discuss how we may implement a closed loop irrigation system for this center pivot irrigation system. Basically, we're going to focus on 2 parts. One is how we can do soil moisture map construction. Another part is on the control part. And for this part is more about state estimation in control. If you know a little bit control, then you must have heard about state estimation. So this part is state estimation, this part is controller design. Okay. And before that, we have to discuss some background of this work. So this map shows the projected water stress, globally in 2030. So the message basically is that by that time, almost all populated areas will face water scarcity. Okay. Maybe not by that time, even now many of these areas have already been dealing with water scarcity. And there are some factors. The main factors contribute to this water crisis include the population, growth, climate change, and the pollution. If we look into the water consumption data, we can find that agricultural irrigation consumes 70% of the fresh water every year. So this is huge, okay, 70%. If we look into the data, we can see that the average water use efficiency worldwide is only about 50% to 60%. So agricultural irrigation consumes a large amount of water, but the water use efficiency is very, very low. And we have water scarcity, this issue. Then one very obvious step is to improve the water use efficiency in irrigation. And for this water consumption, it is also projected to increase further because of population growth. Okay. And before we move further, I'd also like to show you this this photo. It basically shows us what are the typical irrigation methods. So typically we will not get access to this type of introduction, but I think this is a good time just for us to know something different from what we typically see. So for irrigation, traditionally we typically use this surface irrigation flooding like this, right? Still nowadays in many developing countries, people are still using this type of approach. Okay, there's a question, how is water use efficiency is defined? Okay, basically we irrigate and then some of the water will be used by the crops and some will be lost to the underground water. So basically this, the used part divide the overall water applied to the field, and that is efficiency defined. Okay. And nowadays, most of the irrigation methods are like this, either dripping irrigation, like here, or using sprinklers. Center pivot is here, using sprinklers. Now I think we have the sufficient background, so we can talk about some some recent research on this part. So traditionally for agricultural water management, it focused on how to move water from one area to another area to meet regional demands. And in the past decade, then we see more efforts being made to this on-farm irrigation applications. So we consider how water is applied in a farm specifically instead of the regional. We go to the farm directly. And there are indeed lots of papers, lots of work. But if we check this work, we can find this. For these studies, they primarily focus on greenhouses that use drip irrigation systems. And for drip irrigation system and these greenhouses, one feature is that the environment is controlled. The humidity, temperature, you can control of all these. And we may use some point sensors, then we can get some useful feedback information. Okay. But if we consider a farm, for example, the radius is about 1 kilometer, a point sensor doesn't really tell us too much information. And if we consider center pivot irrigation system, that's the case. So it's very hard to get the water distribution over a farm. So the way people do irrigation right now is like this. So the farmer will determine how much water to apply and when to apply the water essentially based on experience. The farmer may also check the weather forecast or visually examine how the crop grows, and sometimes may also go to take some soil samples. But that's all, okay. So they don't really use the real-time soil moisture in the field to make these decisions. And from a systems perspective, this essentially is an open loop decision process, open loop system. And in control, we know open loop system is not precise. Okay. So this will for sure lead to either over or less irrigation, which means the water use efficiency is not that high. So what we are working on essentially is this. We try to implement or realize a closed loop irrigation system. It's a simple feedback loop. Right.
May I have your attention, please? We'll be doing a test on the fire alarm system. Please disregard.
We want to give that test. So the system is just a simple feedback control system. So we have measurements. So first we should have some sensors to measure the soil moisture from the field. Then we then we do a state estimation, try to construct the state of the system, that is the soil moisture map. And then based on this state information, we do control decisions. And these two elements are the topic of today. And first we're going to start with, we're going to discuss this soil moisture map construction. As said before, it is essentially state estimation. Okay. The concept is very simple, state estimation. And for state estimation, typically we need these three elements. The first one is a model of the system, and then measurements, then an estimator. Model, measurements, estimator. The three elements of a state estimator. So we're going to first introduce the model we have developed. So the system we consider is an agro-hydrological system as shown in this plot, right? This figure. Basically, it describes how water moves around the soil and then goes to the crop and then the environment. And what we may also consider this entire system just like it. We don't really have to go into the details. We can just consider it as a black box. So water gets into the system through rain and irrigation, and water gets out of the system through evapotranspiration and also root water extraction. So to model such a system, we need to consider soil water dynamics and crop growth, and also movement of this center pivot. We're not going to discuss all of these. We will just discuss soil water dynamics a little bit. So for soil water dynamics, it's not a new thing. So typically it is described using this Richards equation. Okay, and the Richards equation was developed almost 100 years ago. Okay, it is widely used in this hydrology area to describe water dynamics. It's a partial differential equation. And what we did here is to rewrite it in a different way. So we rewrite it in the cylindric coordinates. So by rewriting it, then we can incorporate the movement of the center pivot into the system much easier. Okay. And earlier works only considered 2D systems, linearized. So no one has done this before. So this is our work. We write it for.
Attention please, testing of the fire alarm system is complete.
Okay, that's quick. So we have written this model. Still, it is a partial differential equation. And after we have this equation, then what we need to do is to discretize it so we can solve the equation, right? And the way to discretize it, so we use the method of lines to discretize this equation, and we approximated the spatial derivatives using the center difference scheme, and then we incorporated crop growth model into the system through the sink term, basically how water is consumed within the system. And irrigation is considered as boundary condition on the top. And then you can see that the boundary condition is actually changing all the time. That's the modeling part. And then for the sensor we use is microwave sensors. These sensors are developed by a startup company. We just partner with them and use the sensors. So these sensors can be mounted on the center pivot. As the center pivot rotates, then you can scan the field and collect microwave emissions. And then from the emissions, it can somehow infer how much water is contained in the soil, the surface layer, how much water is contained. So it's good. It provides a feasible way to get some measurements for a very large field. Okay. You can imagine if we use point sensors, we may need many these point sensors, but for this, it is much more convenient. But at the same time, there's some drawbacks. For example, for the center pivot, because it's very big, so it moves slowly. Okay. For a big farm, it may take 1 to 3 days for the pivot to rotate once. So we don't have very frequent measurements. So that's the modeling and measurement part. For the estimator part, we simply used extended Kalman filter. So this is a popular estimator for nonlinear systems. The only thing we need to deal with in the EKF is the computing side, because the system is very big. We'll see. It's computing and tuning part. We're not going to discuss that today. So we have the model, we have measurements, we have the estimator. Now we can show some results. So what we did is we performed some experiments in a research farm in Lethbridge, so the very south part of Alberta. And in this research farm, we consider this field. The radius of this field is about 300 meters. So not very big, but it's a big farm. And for the microwave sensors, the measurements are indeed quite noisy, so we also did not have data pre-processing. We're not going to discuss, but after processing, so there's still some measurements that we can use. So for this specific farm or field, we considered here we just show a quadrant or a quarter of the field. So 90 degrees. So the field radius 290 meters, and we consider the soil depth 0.6 meters, 60 centimeters, not very deep, but this is good enough for crop growth because the major roots are in this part. And then we discretize the system. In this R direction, we use 30 nodes. In the theta direction, 17. And for the Z direction, this depth direction, this is indeed the most important direction, so we used relatively a little bit more, 10 nodes for 60 centimeters. So after discretization for this 1/4 of the field, it has over 5,000 nodes. So it's not a simple small system. And crop information was incorporated, and the crop considered for this quadrant was barley. And the measurements from, it was 2019, the summer of 2019, okay, before the pandemic. So we used that. And for the parameters, so we simply used what the farmers told us as clay known. So we Googled what are the parameters of this soil type and then use those parameters in the model. These figures show some of the results or the plots we have obtained. From these plots, we see that we can actually see the movement of the center pivot. Okay, so here we have measurements. Then we use measurements to update the estimates, and then here we have measurements. We update the measurements. Then we see that these reflect the movement of the center pivot. In systems or in control, we know if as long as we have a model, we can do lots of things. For example, we can use a model to do prediction. We can use a model to do a state estimation. So we can do lots of things. But for this irrigation, this specific problem, previously this is not possible. Okay. For example, for the microwave sensors, they can collect data, but it takes 1 to 3 days. After 3 days, they have a set of data, and that's it. And the data are collected from different times, so it was not easy to use. With the model, then we can show the farmers frequently updated soil moisture distribution. Okay. This is something new for the irrigation part. And we did some validation just to see how the model works. In the first set of validation, we kept, for example, we used 80% of the measurements to update the EKF, the estimator, and used 20% just to validate the results. This plot shows one set of the results for this specific date. And the red dots are the estimates, the blue dots are the measurements. We can see that the trend is overall kept very well, right? And we also calculate the normalized root mean square error. It was about 28%. Not small, okay? Not small. But the trend is overall captured. This is indeed very encouraging. So the first run, we have a model, then we use EKF, a very popular one, then we put it into the system, and then we got some results. And turns out, not too bad. It's very encouraging. And we did another set of validation as well here. So in this type of validation, what we did is we tried to test the prediction performance of the system. Okay. So what we did is we used the measurements from 1 day for validation. So the 100% measurements from that specific day was used for validation. So no measurement was used to update the EKF. And the previous measurements were obtained a week ago. This means the EKF was updated a week ago. Then we simply use the model to do open loop prediction for 1 week. And then this shows the results. So this is the actual measurements, and this is a prediction, and there's a difference between them. If we look at this, I don't know whether you can see the small fonts here, but the biggest difference is about 0.1, and the actual value is about 0.3 something, less than 0.4. This means the maximum mismatch is about 30 or 35%. But if we look at this part is pretty much very small. Okay, so which means even over 1 week, the prediction was good. So this is again very encouraging. So the irrigation system, I think, itself knows they need our attention. Okay, so it's a very friendly system. As long as we do something, they give us some good results. So it doesn't disappoint us. And we further analyzed what may cause this issue. Then we went back to the soil parameters, because the parameters we put into the model was simply we Googled from the line for that specific soil type. The soil type of the field may change over different locations. So what we considered is to go back to the field and identified some points with poor estimation. So we went back to the field and took some samples. You see, the students are very happy to go to the farm. So it's very exhausting to take samples, but they were very happy. But the results turned out to be not that great. So the normalized IMSC reduced from 28% to 24%, a small improvement, not that good, right? Then what we consider is what else we can do for this specific system, what extra information we can extract from the measurements. Then we considered parameter estimation. Okay. So maybe the parameters we get from the field is not really that helpful for this estimation problem. Okay. Then we considered simultaneous soil moisture and the parameter estimation. And for the system, for soil hydraulic parameters, so typically we have 5. Okay, we don't have to worry about what are these 5. And for each node, we consider the node may have different parameters. So in total, we have many parameters. Okay, but we only consider the surface nodes. So in total, we have over 2,000 parameters. But for this many parameters, for sure, we cannot estimate all of them, right? Then what we did is we performed a sensitivity analysis. We calculated the sensitivity of the measurements to these parameters, and then try to find which parameters may be estimated, or we have the best chance to estimate them. Then we performed orthogonalization to determine these parameters. And after all these, we're also using interpolation. Basically, if we have some parameters updated or estimated, then we use interpolation and try to interpolate the rest of the parameters. And after doing this, the results turned out to be much better. Okay. And the normalized IMSC is reduced from 0.28 to 0.16. 30% improvement. That was great, right? And further we check the estimated parameters, and we want to see whether these parameters actually make sense. And we estimated parameters, then are they actually make sense? Here shows some results for one of the parameter Ks. So for the initial guess we used is some value, we put it everywhere. And after some time, these two plots basically shows us the estimates for these parameters has converged. Okay, they are very similar after some weeks. And these values we see they are indeed very close, about 0.3. Okay, 0.3 is very different from the initial guess we gave the system. And in order to verify whether these estimates are reliable, we again went back to the farm and took some samples and then did some analysis. To find these parameters, it needs different procedure. We didn't know, so we went back to the farmer again and took samples And from those samples, we only have 6 or 8. From those samples, we found the mean KS is about 0.376. Then what we can see, this value is indeed very close to this. So from a very different initial gas, we went to this value. This value is from Google. Okay. So from online information, we went to some value that is very close to the actual value. So this is indeed, I think it's indeed very, very good. So this is an estimation work we have done so far, and then we can move to the irrigation scheduling or the control system design part. So for the irrigation scheduling or control problem, there are a few objectives. For example, we need to ensure the crop yield. This is obvious. So to ensure this, basically we need to make sure the root zone soil moisture is within a certain range. So there's no water stress for the crop. And we want to conserve water to reduce energy consumption. So different objectives. And what we can manipulate are these. So when to irrigate. So when to start the center pivot. It doesn't move all the time. So when we want to irrigate, then we start it. Then it starts irrigation. And when it starts, how much to irrigate? Okay. So for the first one, when to irrigate, typically it's a daily decision. And for how much to irrigate, then you need to consider when center pivot moves a little bit, how much you need to irrigate. This typically is an hourly decision. And this is continuous, this is integer. If we consider the system we have, if we want to put everything into one optimal control problem, then this is very challenging, okay? Because the size of the system and also the center pivot is rotating. So what we did is we use the knowledge we have gained from process control, from many control problems. Basically, we just simplify the problem and separate scheduling and control. Okay. So we separate the overall problem into daily scheduling and hourly control. And today we're only going to talk about this scheduling part. And in the scheduling, if we want to control the 3D model directly, it is also very challenging because we have integers and the system is big, it's nonlinear. So what we did is we tried to further simplify the problem. The way we try to simplify the problem is try to divide it into different irrigation management zones. Okay. The way we do this is first, according to the different crops, we separate the field into different quadrants. Typically, for a quadrant, different crops will be planted. So different quadrants, and then within the different quadrant, we use the soil hydraulic parameters. We estimated them, right, in the first part. So based on the estimated parameters and also field elevation, we try to cluster the different nodes into different clusters. And this part, after clustering the different nodes, then we further map these nodes into the resolution of the center pivot. For the center pivot, it can, one sprinkler covers one area, and the resolution is not that high. So, for example, we have one. We can manipulate the input for this small cell, but you cannot do it for smaller areas. So we further map this to the resolution of the center pivot. For example, for this quadrant, we can have 3 measurement zones. And then for each measurement zone, we just consider one 1D model. Okay. We don't consider 3D. We just make it simple. And for the 1D model, we try to use the Richard's equation we showed before directly, but computationally it's very challenging. Then what we did is we try to identify an input-output model using LSTM. So the input is irrigation amount, output is water contained in the soil, in the root zone. Then we, okay, this just shows the way we do the data-driven model. And once we have the model and the management zones, then we try to put them all into one optimization problem. Okay. For example, this part is zone tracking. Is the soil moisture tracking. We try to control them within a range, and this part is the integer when to irrigate, and this part is how much to irrigate, and we put it into one optimization problem. And we have indeed quite a few tuning parameters. If the management zones, the number of the zones are not small, then it's very, again, it's very challenging to tune these parameters. Yep. So here we consider, this shows some preliminary results. We considered one quadrant for the research farm, and we constructed 3 management zones. And typically, the root zone available water, the target is, so we need to, if we consider the farm as a, you see, water balance, if you consider this as a box, for the farmers, they want to make sure that all the time we have at least 60% of the boxes is full. Okay. Now this is a control target. And we consider 2 different scheduling schemes. One is proposed, and we look into the future for 14 days, 2 weeks. And one is a triggered scheme. The triggered scheme, because right now in practice, there's no feedback control system. Okay. But this trigger scheme is similar to what the farmers do right now. They just estimate based on their experience whether they need to irrigate. If they need to irrigate, then they irrigate and try to push this number to 100%. It's somehow similar to this trigger. Okay. So what we have is the best possible scenario for the current practice. Okay. And this slide shows some results. Maybe not that easy to see. But yet, this red means, this red shows when we have irrigation, if we use a trigger scheme. And the magnitude here shows the amount. And the blue is the decision from the proposed optimization. And these black bars are the rain we have for the growing season. So this is an entire growing season for a few months. And here shows the soil moisture trajectory. From this trajectory, basically we see that both approaches can somehow maintain the soil moisture within the target. Okay. But if we look at this, we see that for the proposed, for the entire season, we only used about 884 millimeter irrigated water. Okay. But for the triggered, a little bit more, so we can save about 6 or 7% water for this simulation. But we need more center pivot rotations. So we need 5 more. But if we consider the overall cost, so the overall cost also accounts for these violations of the target zone. Okay. Then the proposed will be much better. And we can, based on this, we can also predict the crop yield. We can see that the proposed, if we do some optimization, then we can also increase the crop yield. Basically, we can use less water and also increase the crop yield. Okay, so this concludes, essentially concludes the presentation. So in this talk, so what we discussed essentially is that we need to close the loop for this very big irrigation system. And what we found is that if we do both state and parameter estimation, then this is a very effective way to construct a soil moisture map. And also we found the scheduling and control problem is better to be separated, then we can have some simpler problems to deal with, more feasible. And optimization also has the potential to balance irrigation amount, energy consumption, and also crop yield. But the tuning, from our experience, tuning is not that straightforward. Okay. At the end, I'd like to acknowledge some of my students and collaborators. So the work shown today has essentially been done by Vlad, who's a PhD student in my group, and supported by a few other students. And also these Professors Rashah and Dr. Mohammed and Professor Apels, they provided lots of guidance and support. And these are the soil water specialists in the research farm. They also provided lots of useful information and funding agencies or partners. And that's all for my presentation, and thank you very much for your attention. If you have any questions, I'd like to discuss with you.
So we thank Professor Liu very much for his presentation. Do we have any questions for him? Yes, please.
Yeah, thanks for your talk. I'm wondering if the model quality was affected at all by the size of the field. So in other words, was a smaller field and easier to model?
I agree, indeed. So for the model quality, what we found is this. So indeed, we don't need this many nodes, you see. Technically or theoretically, if we want to have more accurate results, we should have more, indeed we need to have more nodes. But for the estimation problem we have, for the irrigation problem we have, maybe we don't need so many nodes. So we also have some work that's, some students working on model reduction. Okay, we just try to do some analysis, see which nodes we should use, which nodes maybe we can merge together, right? For this irrigation system, or for this agro-hydrological system, as mentioned, I would say it's a friendly system. So even, well, initially we thought the model we have maybe not that good, but the results turned out to be encouraging, I would say.
So I may have one question about the scheduler. So I'm wondering that if the ASTM model is used in the scheduler for the automatic information, then I see a prediction function big F here. This means the ASTM model?
Yeah, you mean this big M?
No, the big F.
Big F?
Yeah,
this is a data-driven model, LSTM model. Yes.
Yeah, so which optimization solver do you guys use to solve this problem? I mean, it's very hard to solve it when you use ASTM model.
So for this, that's a good question. So this is an overall optimization problem we want to solve. Okay, and we did lots of simplifications. Okay, we try different ways. For example, we have integers here. We have nonlinear systems.
Yeah.
We tried some nonlinear mixed integer solver, but that doesn't really work. Okay, and then we try to use, for example, some sigmoid function to approximate this integer decision, and then use IPOP to solve it. And we're also trying to use, for example, we just replace this not necessary LSTM. We may identify a ReLU neural network and try to convert it to mixed linear integer problem. So we're trying different ways. And we also tried, so lots of background work, we also try to further simplify this or decompose this into different optimization problems. Okay, that's a good question.
Yeah, and also another really question is why do you use ASTM for the state estimation and also for parameter estimation?
Okay, that's a good question. That was also something we considered, long time ago. For estimation, what we found is we have measurements for the microwave sensor. What we found was this. As said, the measurements are kind of noisy. The usable measurements at each sampling time are from different locations, so it changes all the time. And for the 3D model, seems okay. I mean, the computationally seems okay for estimation. So we didn't go further, for example, to simplify the model further. But for control, because we cannot handle this optimization problem, then we try to simplify it.
So we have a question from Alan. He's saying, have you done any validation by measuring the water status of the crop itself, which is of course the central goal of irrigation?
Okay, that's a good question. So we haven't checked the health of the crop directly, but we have some other sensors also in the field. So those probes, so just point sensors in the field, we used those sensors to check the estimation results as well. Also, we use those measurements to check the accuracy of the microwave sensors as well. So basically, what the conclusion, so I didn't show that, but the conclusion is that the microwave sensors basically give us somehow reliable measurements, can overall track the trend of the change of the soil moisture. But how to, no, but that is a good question. I think to check the health or the actual yield of the field, that could be the next step.
Yes, Michael.
I had a question about the finite element model. So you found that there's elevation differences in the field, and I'm wondering how that affected because it looked like the finite element model was perfectly flat. So.
That's another good question or good catch. Okay. So for this field or for this research farm, we picked one that is kind of flat, and we try to consider slope in this 3D model. It's very challenging, and the approach so to handle the slopes, one way we think it might work is to classify the field into different measurement zones, like in the irrigation part. In the irrigation part, we considered different the elevation data in deciding the measurement zones. So that may be one way we can use. But to have the slope, for example, in this model, we found it's very challenging. There's some commercial software that can do this, but it's not easy to use those software in, for example, estimation or control.
Thank you. And one more question, like near the surface, that zone seems to be more dense. And was there some model of like the roots absorption incorporated there, like the sink strength or the low pressure provided by more dense roots in that region?
That's a good observation. Yes, so the discretization for the top parts is more, it's finer. Because when we put water to the field, then we will see it changes quickly over this portion. And then later it propagates to the lower, deeper layers. So it takes, we found this part is critical in obtaining a reliable model. So we need to have smaller cells in order to have to make sure the accuracy is good.
And the irrigation and the evaporation are from the boundary conditions at the top?
Irrigation is from the boundary, but evaporation is from the crop, so it's in the crop model. And for the crop roots, the root water extraction is mainly from the top to somewhere, I would say maybe over here.
I'm curious about the disturbances and disturbances. will affect the irrigation area and also soil nutrition?
That's an excellent question. Yes, for this, this is open system, open environment. So we have lots of these disturbance for the wind speed. When you irrigate, if there's wind, actually water will go to somewhere you don't know where. So in the model, in the model, in the estimation, we haven't considered these disturbances explicitly. Okay, but what we did is, so in the farm, in the research farm, there's another team from Bridge College. They try to make the irrigation data and all these measurements as accurate as possible. When the wind speed is over a certain range, then there's no irrigation for sure. And when the wind speed is acceptable, then they do the irrigation. And also, there's some in-field sensors for them to measure how much water is actually irrigated, and also the weather, as a local weather station, just to measure the ET temperature of those. So there's some work try to minimize those disturbances, but unavoidable.
I think, sorry, but we're out of time. So you can have one-on-one conversation with him later. So thanks very much, Professor Lee, for joining.